So good evening, everyone. I'm delighted to welcome you all to the Geological Society's Lyell Medalist Winner Lecturer with Dr. Bill Ryan. The Lyell Medal was established under the will and codicil of Sir Charles Lyell, who was the author of Principles of Geology, which popularized the idea of uniformitarianism. And the Lyell Medal is a very highly regarded international prize. My name is Professor Graham Shields. I'm Professor of Geology at UCL and a member of the Geological Society's Science Committee. I'd like to introduce you today to our speaker this evening, Dr. Bill Ryan, who's joining us from New York. Bill taught at Columbia University until his retirement in 2021, and his research includes investigations of mid-ocean ridges, submarine canyons, underwater volcanoes, escarpments of limestone that are our planet's tallest cliffs. However, you might know the name Bill Ryan for another reason, because in the heady days of plate tectonics back in 1970, he co-led a famous cruise of the deep sea drilling project on board the Glomar Challenger, where they discovered some early evidence for subduction, but also, very importantly, evidence that the Mediterranean Sea had undergone restriction and there were deposits kilometers thick of salt, and that's today known as the Messinian salinity crisis. Dr. Ryan's team developed deep-towed side-looking sonar that located the RMS Titanic far from its distressed position. His group then used that instrument to image seabed, volcanic lava flows, giant landslides, grooves left behind by ice age, icebergs, and deformation, where one tectonic plate slides beneath another. Tonight, Bill will discuss from catastrophism back to uniformitarianism. This lecture will take us through this 5-decade journey of research that in just the last few years rehabilitates Charles Lyell. And we will uncover evidence of desiccation in flooding in operation today in the Dead Sea. So it just remains for me to give you the floor, Bill, and thank you so much for joining us this evening, and congratulations on your award. And just before we start, though, there will be a 15-minute question and answer session at the end of Bill's presentation, so please post your questions in the chat box. Finally, this lecture will be recorded and uploaded on the Geological Society's YouTube channel. So without further ado, over to you, Bill. Thank you.
Thank you for the introduction. Charles Lyell was a Scottish geologist born in 1797, who is now best known as the author of the 3-volume Principles of Geology, published between 1830 and 1833. An early draft was taken by Charles Darwin on his voyage on the Beagle. His volumes gave the wide public audience evidence that the Earth in the past had been shaped by the same natural processes still in operation today, and most importantly, operating at similar intensities. He abhorred the concept of catastrophism, adopted by the diluviists, and propounded instead the doctrine of uniformitarianism. In building upon the innovative work of James Hutton and his follower John Playfair, Lyell favored a long age for the Earth. Lyell entered Exeter College, Oxford in 1816 to study classics, where in the course of his studies, he attended geological lectures of William Buckland. After graduating, he took up law as a profession, but during his travels through England, he could not help himself observing and contemplating geological features and ways to unravel their ages and origins. William Buckland was at that time the most influential geologist in England. His inaugural lecture as professor of mineralogy and geology at Oxford was entitled "The Connection of Geology with Religion Explained," wherein he attributed all of the widely scattered and unstratified deposits throughout England and Scotland to the ravages of a universal flood of Noah. Buckland believed fervently that the purpose of his science should be nothing less then to conform the evidence of natural religion and to show that the facts developed by it are consistent with the accounts of creation and deluge recorded in the Mosaic writings. Upon graduating with his master's degree in classics, Lyell attended Robert Jamieson's lectures in Edinburgh, where, coming under the influence of James Hutton's prior thesis that the physical world's remote history can be inferred from evidence in present-day rocks. Here in Sicker Point, we observe this extraordinary unconformity between flat-lying or mostly flat-lying rocks of ancient age above much older vertically stratified rocks, 70 million years earlier, with a huge span of time in between. He put forward the view that what has actually been, we have data for concluding with regard to that which is to happen thereafter. And Lyell put aside all that he had learned from William Buckland. No vestige of a beginning, no prospect of an end. Lyell began his travels, and here in a sketch in the frontispiece of volume 3, he is viewing the Pyrenees in the background from Catalonia, Spain. And in blue are the distant Pyrenees that consist of ancient primary rocks. Closer on are younger sedimentary strata. And in the foreground are the younger tertiary sedimentary strata that Lyell would explore and explain thoroughly in his volumes. The succession of ages was apparent, but how to apply a geological time scale became his passion. And throughout his life, Lyell kept a remarkable series of nearly 300 manuscript notebooks and diaries, which allow us to enter into his deep thinking. Here he collected fossils of mollusks, gastropods, that he considered were the most recent strata or rock layers that could be categorized according to the number and proportion of marine shells who resembled those that were living today. He assigned them to his Pliocene epoch, with the name Pliocene adopted from ancient Greek, plion kainos, meaning roughly continuation of the recent. Those species somewhat similar to those today, but not quite as close, he placed in an earlier Miocene epoch, from the Greek word meaning less recent. And those, unlike any of the younger species, he put into his Eocene epoch, using the Greek word for dawn, and for Lyell, the beginning of his tertiary period. His new epochs can be ordered, all belonging to his tertiary period, with locations of where he collected his shells. I attended Williams College, nested among the Purple Mountains belonging to the Taconic Range of northwestern Massachusetts, and the product of mountain building ending about 440 million years ago. I graduated in 1961, 140 years later than Lyell, with a bachelor's degree in physics and math. I took a single semester course in physical geology, where we were educated in the geosyncline theory of mountain building, greatly simplified here. The process starts off with a deep basin called a syncline that begins to fill with sediments shed from neighboring mountains. And then it fills with sediments over the span of many, many millions of years, until eventually the sedimentary layer gets so thick that heating from below causes the crust to rise up and expose all these sediments to terrestrial erosions. And what's left behind from the erosions are the mountains that we observe, hike in, and ski in the winter. But I was never comfortable with this idea. By what physical process could we observe today produce such synclines? Upon graduation, I had the fortune to be hired at the famous Woods Hole Oceanographic Institution on Cape Cod. At this moment, the geophysics department was engaged in research funded by the US Navy. And my superior was using acoustics to decipher the properties of the ocean interior and its seabed sedimentary strata. I was assigned to the electronics shop to help finish the construction of a new device that would use extremely powerful sound waves to image the sedimentary layers that accumulated on deep seafloors of the Atlantic Ocean and Mediterranean Sea. In July of that year, we set sea for a 6-month expedition on the research vessel Chain. The Chain towed behind it a source that emitted powerful explosions of sound, compressive waves that traveled to the seabed, bounced as echoes off the seabed, and returned to a string of hydrophones towed behind the ship. The waves were sufficiently powerful to penetrate through the sedimentary layers and return echoes of the ocean bedrock crust below, and even get echoes from all the thin layers of sediments that covered the drape over the bedrock of the ocean. I brought with me the physiographic diagram of Bruce Hazen, Marie Tharp, and Morris Ewing, published just a few years earlier in a volume called The Floors of the Oceans, as its centerpiece. We departed Woods Hole and crossed the continental margins, the shelf slope and continental rise, entered on to the Somme abyssal plain, crossed the Bermuda Rise, the main part of the abyssal plain, climbed up the flank of the mid-ocean ridge, crossed its axial rift valley, and then down the other side and into the Mediterranean. And looking at the reflection profile from the abyssal plain, we could detect echoes from the seafloor, echoes from the bedrock, and echoes from the sedimentary strata in between, with a sedimentary layer over 2 kilometers in thickness, representing an enormous span of time. Approaching the flank of the mid-ocean ridge and just leaving the abyssal plain, the sediments were thinner, and what was missing was all the earlier deeper strata that we had seen earlier. Climbing up on the flanks of the mid-ocean ridge, the sediments only were there preserved in deep pockets beneath hills of the bedrock. And arriving at the axial rift valley of Marie Tharp's, we took a deep sea camera system and with a very powerful flash, an electronic strobe housed in cylinders with steel walls 1 inch thick, a lens of glass 2 inch thick to keep away the deep pressures of the abyss, and sent it down for a trip lasting over an hour to then expose the seafloor. And what came into view were volcanic deposits of lava that had oozed out of an axial fissure in long tubes that ended in pill shapes, whose skin then rapidly froze in the abyssal cold water. No sediment, just a slight dusting, perhaps of the last year or two. This insight was immediately digested by us aboard the ship as indicating that the axis of the mid-ocean ridge was exceedingly young and that the basin's two sides was old. and that the ages got older and older away from Retharp's axial rift valley. And so the sediment thickness gives us a sort of a age clock from young to old as sediments accumulated through time. A year later, I found myself at Columbia University entering a graduate program in geophysics in the Department of Geology. My mentor turned out to be Bruce Hazen, and I had an office right next to that of Marie Tharp. Here they are pointing to a proof of their brand new physiographic diagram of the map, pointing to the axial rift valley that went down through the entire Atlantic Ocean. I set out to do a thesis research on the Mediterranean Sea because I had spent many summers since 1961 aboard research vessels of Woods Hole, Lamont Geological Observatory. And using soundings collected by these expeditions and soundings from European expeditions and older maps, and especially a huge amount of soundings from the Navy's laboratory, the NATO laboratory in La Spezia, I sketched what we could presume was the seabed of the Mediterranean Sea, along with the help of Marie Tharp. And we took these sketches to Innsbruck, to the artist Heinrich Baran, who then painted this marvelous panorama as funded by Der Stern magazine in Germany for the centerfold of their 20th anniversary issue. The Eastern Mediterranean has the extraordinary ridge in its center, and our reflection profiles across the ridge showed that the African side on your left was essentially being squeezed against the European side on your right. And the sedimentary layers were being buckled and compressed into an enormous high ridge of folds and thrusts. A similar squeezing had been observed by a fellow graduate student, Phil Rabinowitz, in front of the Antilles Arc of the Caribbean Sea. And a new seismic profile from Woods Hole by Dick Chase and Betty Bunce showed that the sedimentary layers of the Atlantic oceans were actually being thrust under this wedge of sediments in a process that took the upper layers and scraped them off to become what we now call an accretionary prism, the first hint of a disappearing ocean floor. Precisely at this time, Walter Pittman was aboard the RV El Tanin en route from Valparaiso, Chile to Auckland, New Zealand. In an unknown, poorly charted regions of the Southwest Pacific Ocean, he discovered a ridge that looked remarkably similar to the Mid-Atlantic Ridge and was situated halfway between New Zealand and Antarctica. Along with seismic reflection profiles that showed the thinning of sediments as he climbed up the ridge, Walter had magnetic anomalies from his recording of a magnetometer that he had helped construct that was being towed behind the El Tanin to keep it away from the magnetic signature of the ship's hull. And he noticed that these magnetic variations increased in amplitude as you got close to the crest of the ridge and then decreased down the other side. But there was a very strong positive anomaly or reading right at the axis of the ridge, which was exactly the situation that had been found and published in 1959 by Hazen, Tharp, and Ewing. In looking at details of this anomaly, Walter realized that the axial anomaly was flanked by ups and downs that looked remarkably similar on the two sides. He flipped his profile, and indeed they revealed the identical pattern of strong magnetism and weak magnetism. He then synthesized, he took postulate that the upper 2 kilometers of the volcanic bedrock of the ocean had been magnetized in the direction of today's field when the Earth's magnetic field pointed to the North Pole, but had been reversed in the opposite direction when compasses back in those times had pointed in the direction of the South Pole, using a concept that had been pioneered by Fred Vine and Drum Matthews at Cambridge University. And his synthetic profile generated signals that looked exactly like his original. Walter and his advisor, Jim Hertzler, had come across a new time scale using magnetic reversals that aged away from the ridge axis, just as had the sediment thickness. The publication of this in 1966 created an extraordinary conversion of scientists away from resistance to continental drift to acceptance of seafloor spreading, and then on to plate tectonics. To test the Pittman-Hertzler hypothesis, the National Science Foundation chartered a brand new drill ship, the Glomar Challenger, to go to sea and drill down through the sedimentary layer. The Challenger carried 5 miles of drill pipe on its foredeck. Arriving at a site, usually located according to a seismic reflection profile, an acoustic beacon was dropped that sent signals back to the ship that could allow the ship to stay with thrusters in exactly the same spot for days on time. It took hours and hours to put the drill pipes together, reach the seafloor, and then every 2 hours receive a core deeper and deeper and deeper into the sedimentary layer until eventually arriving at bedrock. Here we can imagine the seismic profile penetrated by the drill and the succession of cores, when opened in the ship's laboratory, revealed not only their color, but their mineralogy and their composition, even the direction of magnetism that had been remembered in these sediments, and the range of species of tiny planktonic organisms, foraminifera, and coccolithospheres. Their extinctions and their first appearances allowed us to put a timescale together using the epochs of Charles Lyell, Pleistocene, Upper Pliocene, Lower Pliocene, and Miocene. This technique was quickly applied to the South Atlantic to drill gradually at further and further distance away from the axis of the ridge, and use the first sediments on top of the bedrock, the age of those sediments, to plot their age on the vertical axis as distance from the mid-ocean ridge axis. And lo and behold, they lined up on a straight line, just as had been predicted by Pittman-Hertzler. And so today we have an age map of the oceans, going from youngest at the center to oldest at the margins in millions of years. A few years later, I found myself invited on the first expedition to the Mediterranean, along with Ken Su from the Federal Institute of Technology, ETH, in Zurich, to explore not only the convergence that we had seen in the Eastern Mediterranean, but these strange knolls that poked up in the seafloor in the Western Mediterranean. First noticed as early as 1957 in crude echo soundings by Jacques Cousteau and his co-workers from the Oceanographic Museum in Monaco. Our reflection profiles show that they were protrusions up through the sedimentary layers into the seafloor, presumably from a deep layer of salt. We didn't drill there because hydrocarbons are often associated with salt domes in places like the Gulf of Mexico. So we picked a site between the Balearic Islands and Catalonia, Spain, where there was a buried reflector that I had named the M reflector. It displayed some evidence of erosions and curious channels. Targeting our drill site in one such channel, hoping to reach it, sample all the sediments on the way down into the bedrock. As we approached the contact with the Mediterranean, the M reflector, I went out on the derrick floor to observe what was going on there. Suddenly, alarms went off. The drilling supervisor became very concerned. The motor that was turning the drill pipe was straining, and suddenly the rotation stopped altogether. Sediments had collapsed upon the drill pipe and had frozen it into the seafloor. Hours were spent pulling on it, until eventually, luckily, it came free. When the drill pipe arrived and was all laid out on the 4 racks, the drill bit was inspected, and it and the neighboring pipes were full of tons of pea-sized gravel. Buckets of gravel were delivered to me in the ship's lavatory. I washed it and looked at it. It was weird. Only 4 components. Basalt, volcanic rock, presumably eroded out of the bedrock. Limestone of an age 3 times greater than our Pliocene sediments. And crystals, translucent crystals of gypsum, a mineral that evaporates from seawater under extremely high evaporated conditions. And lastly, fragments of shells that belong to species of mollusks that Lyell himself had recognized in his studies in southernmost Sicily. These species, rich in bivalve fauna, were dominated by fresh and brackish water fauna. And most diagnostic was this melanopsis that Lyell himself had assigned to the Miocene epoch in volume 3 of his Principles. And most puzzling was this tiny mussel, Dracaena rostriformis, that had apparently traveled all the way from Caspian and Black Sea lakes to the Western Mediterranean. Knowing that we could not drill in channels, we picked a drill site east of Minorca, where the M reflector was flat, and we could penetrate it through, hopefully without problems, maybe even pass through the salt layer and reach the bedrock. But once again, going to the rig floor as we reached the M reflector, having just recovered a beautiful core of earliest Pliocene marl, the ship began to shake and shudder as if the drill pipe had reached solid rock. I knew it could not be bedrock, which would be far below. And so I ordered the cutting of a new core. And when it arrived and was opened in the lab, it is this extraordinary white rock. layered, but containing all these nodules, white nodules. Kensu put the rock to his lips and immediately exclaimed, anhydrite, a mineral that's created by the evaporation of seawater under extremely high temperatures, exceeding 40 degrees centigrade or 104 degrees Fahrenheit. And it contained very fine layers, laminations, that might even be annual precipitates. It was populated by these tiny white nodules that had grown into the rock by the crystallizations of anhydrite. The large nodules resemble those that had recently been seen in trenches on the coast of the modern Persian Gulf, in the proximity to the shoreline in what is called the supertidal flat. And here we were with this facies thousands of meters below the surface of the Mediterranean. In finely laminated sediments between the anhydrite layers, we found diatoms. Diatoms require sunlight. And these diatoms were not only bottom dwelling, indicating fresh water, but in a sunlit, shallow river or river mouth setting. Later, towards the end of the expeditions, we found a drill site west of Sardinia with hopes to reach the layers that we thought to be salt, and picked a drill site that would go through the M reflector. And when it arrived at the top of the salt layer, the cores that came up had solid rocks that had been partly dissolved away. It turned out to be halites, sodium chloride, also finely laminated, just like the anhydrite. And when examined under a microscope, contained crystals that contain bubbles with the original brine in the bubbles. Lo and behold, a sandstone, possibly deposited by winds, had a crack in it, resembling the kind of desiccation cracks you see on the surface of a salt pan when it evaporates to dryness. So we put together on our trip back to port a sketch with salt pans on the floors of all the deepest areas of the Mediterranean, proposing that there had been drying up and desiccation to form this salt layers in salt pans. We then published our results in Nature, late Miocene desiccation of the Mediterranean Sea, to a world of skeptics. There was a big pushback, even scientists calling our desiccation theory all wet. But even more significant than this evidence of salt pan halite salt were our cores that had reached the M reflectors in the eastern, central, and western Mediterranean, and had sampled the sediment lying directly upon the lake deposits. Here, a site in the eastern Mediterranean, central Mediterranean, and western Mediterranean. And the cores returned an extraordinarily sharp contact, less than a millimeter in thickness, between shallow freshwater to brackish lakes and deep seawater, saltwater sea. Whatever barrier had existed to permit the drying of the Mediterranean, it had suddenly broke open, and saltwater had flooded into the Mediterranean, bringing its surface back to that level of the Atlantic oceans. and would be called the Zanclean Deluge. When published also in Nature by Judy Mackenzie, the catastrophic flood when Atlantic waters re-entered the Mediterranean corresponds to the boundary between Charles Lyell's Miocene and Pliocene epochs. In Atlantic Monthly magazine, we see tourists out at the Rock of Gibraltar, gazing at this giant saltwater waterfall entering the Mediterranean. Our hypothesis of multiple fillings and dryings and multiple fillings and dryings of water entering in from the Atlantic Ocean to produce the enormous 1,000-meter thickness of the Mediterranean salt layer was really quite outlandish. How could we have so many openings and so many closings without the barrier being interrupted, broken? Decades passed because it was impossible with existing technology to actually drill deep into the salt layer and reach the sediments beneath it. But at the beginning of the 20th century, interest began to grow in the possibility of there being significant petroleum deposits in the easternmost Mediterranean off the coast of Israel and Lebanon. Seismic reflection profiles obtained by these surveys of the oil companies and made available to me by the Geological Survey of Israel showed an enormously thick salt layer, almost 2 kilometers in thickness, lying beneath the sediments, overlying sediments in the seabed. An industry then, shortly afterwards, drilled the Dolphin exploratory well through the salt layer into the sediments below to successfully reach deposits of natural gas thousands of meters further down. A young graduate student, Aaron Millison, at the University of California, at the University of Colorado, Boulder, Colorado, had been able to obtain samples from the sediments just below the salt layer. And they showed that its age was 5.97 million years, 400,000 years older than the surface salts that we had sampled on a Glomar Challenger, that dated to 5.5 million years. And then the lake deposits, the evaporating lakes that ended by the abrupt return of salt water 5.33 million years ago. His paper in the Geological Society of American Bulletin provided evidence that resolved the 50-year-old debate of whether the Mediterranean salt had formed on shallow salt pans like those in the in California or under a thick column of salt water. And it essentially showed that the Mediterranean remained full of evaporating brine during this 400,000 year period and only had desiccated in cycles between dry and wet in the last few 100,000 years. Charles Lyell, in volume 1 of page 298, volume 1, wrote, "It is well known that a powerful current sets constantly from the Atlantic into the Mediterranean. Evaporation carries away only fresh water, and the current is constantly bringing in salt water. What then becomes of the excess salt? The whole Mediterranean ought to become as much saturated with salt as Lake Aral or the Dead Sea. Evaporation begins rapidly, but surface water becomes impregnated with an excess of salt. And as specific gravity thus increased, it settles to the bottom And by the continuance of this process, additional supplies of brine are annually carried to deep repositories into the lower strata of water, are fully saturated, and precipitation takes place. Not in thin films, but on a grander scale, continuous masses of pure rock salt extending perhaps for hundreds of miles in length. Let's look at the Dead Sea. It's now being extensively measured, looked at by strings of sensors that measure its temperature as a function of depth into its highly salty brine. And what these instruments show that in the warm summers, the upper layer becomes extremely warm and becomes separated from a colder, deeper layer by an extremely sharp interface, sometimes only a meter in thickness. The salt crystallizes at this interface, forming these hopper crystals that we had observed on the Glomar Challenger. The upper layer then becomes undersaturated, and the colder, deeper layer becomes supersaturated. If we look at this, salt water from the oceans comes in, it's heated, it evaporates. A warm upper layer appears, salty but undersaturated in brine, above a cold, supersaturated layer. If we look at this interface, it actually develops fingers of warmer brine sinking into the colder brine below, and colder fingers penetrating up into the warmer brine. And the cooling of this warmer brine crystallizes the salt, and it settles in crystals to the seabed to form the, excuse me, whoops. Do I go back? Well, hold on. Which slide do you want? That slide. Right. So now do let's go to this slide. Animate. It develops fingers that actually can be observed in laboratory experiments, and fingers that can be simulated in computers, with the warm fingers penetrating into the colder, deeper layer, and colder fingers upwards. Cameras lowered into the Dead Sea capture the actual crystallization of these salt crystals, and they're settling to accumulate on the bottom. So in conclusion, my salute to Sir Charles Lyell. During your late Miocene epoch, almost 1 million cubic kilometers of salt was deposited on deep floors of the Mediterranean Sea. The event is now explained, as you once wrote, by causes now in operation. I have many colleagues to thank and acknowledge during my lengthy career, but for this tale today, I'd like especially to acknowledge Ken Sue and Maria Chita, who just celebrated her 98th birthday this month. Thank you.
Thank you, Bill, for that absolutely fascinating talk. I think it may take some time for questions to come through in the Q&A session, because there may be some coming through YouTube or through the chat or the Q&A, so might give it a little bit of time. So if anybody does have questions, please put them into the chat or YouTube, and I will endeavor to read them out. In the meantime, Bill, maybe I can ask you a brief question. So the two things that you were researching back in the 60s and 70s, they were very controversial. And you sort of touched on that a little bit, both the Messinian salinity crisis, but also fledgling plate tectonics and continental drift. Could you give us a flavor of what the objections were to the Mediterranean drying out, and how heated it got back then?
When I entered Columbia University in the Department of Geology, all our professors were adamantly against the concept of continental drift as put forward by Alfred Wegener. The geophysicist Morris Ewing had his most objections on the fact that very powerful earthquakes, giant earthquakes, sent their waves ringing around the earth, causing the earth actually to ring like a bell. And therefore, the interior of the earth must be absolutely solid as a bell, and therefore could not permit these continents to move across its surface. So when the magnetic anomalies were discovered, the symmetrical magnetic anomalies were discovered, it created a big stir. And I remember Walter Pittman, after presenting his discovery at the AGU meeting, American Geophysics meeting in Washington, finding his own professors at Columbia University not even believing what he had presented. And so, but for the rest of the geological community, I think the conversion to seafloor spreading was almost instantaneous. And then a spreading ocean explained the surface of a lithosphere moving as rigid plates. So there were a few holdovers. Our own director, I think until his death, never really accepted seafloor spreading.
Thanks, Bill. I have a couple of questions here that I will read out. There's one in the chat. You might be able to see it. If I understand it right, the M layer records a time when the terrain was on land. So if so, how does one measure the time it was on land? Could it be a long time with no deposition? So a hiatus is the question.
No, the M layer was always down in the deep abyss. With its sediments, earlier sediments above the Mediterranean's bedrock. The M layer only became land when the water above evaporated away to expose those sediments belonging to the M layers to desiccation and then precipitation of gypsum, anhydrite, and salt in playa lakes.
I have one more question from Eugene O'Connor. The Dead Sea is a smaller body of water that is cut off from the oceans. Is it a good example to explain what happened in the larger Mediterranean, which is joined more permanently to the Atlantic?
That's an interesting question. The Dead Sea is fed today by the Jordan River, which does not bring in a lot of salt. But because much of the river has been diverted to irrigation, it no longer comes in at the rate that it used to. And therefore, the surface of the Dead Sea is actually dropping by a foot or so almost every year. And so the shrinkage of the Dead Sea is allowing its salt body to concentrate to the level of saturation. For the Mediterranean, the salt is delivered from the Atlantic Ocean, essentially through very narrow straits that we think cut across southern Spain and northern Morocco, straits that would have been no deeper than tens or so meters in depth, feeding salt water to the Mediterranean at the rate that it was evaporating. And so this continuous supply of salt and continuous evaporation led to saturation and then precipitation of the salts through this period of 400,000 years.
Okay, just got one more here from Ole Martinson. An absolutely fascinating talk. Thank you so much. A simple question. What is the total volume of salt deposited? And the way I read your sketch, you had 3 or 4 smaller basins where the salt was also deposited. Were they set upon weaker crust and thus deeper?
These different basins were not set on crust that was necessarily deeper. They were set on crust that was of different ages. The Western Mediterranean crust was just about 25 million years in age. The Central Mediterranean crust was only about 8 or 9 million years of age. And the crust in the Eastern Mediterranean was perhaps as old as 160 million years. These were floors that were already deep at the time of the salinity crisis.
And a question from Kim Castens. Do you think that 21st century geology has reached the appropriate balance between uniformitarianism and catastrophism? For example, between trying to explain everything in geological history with current processes and requiring extraordinary causal processes? It's quite philosophical.
Well, we're seeing, somewhat catastrophic processes occurring today in powerful hurricanes and in rising sea level. But these hurricanes are also recorded in the sedimentary deposits of the past, and sea level change has been observed. Remarkable sea level change, a drop of sea level of the magnitude of 120 meters just in the past ice age, 15 to 20,000 years ago.
Okay, I had one other question, and that was quite recent, the late Miocene. Are there any good analogues in the much deeper geological record for the Messinian salinity crisis?
Oh, yes, several fascinating examples. When the South Atlantic first split apart, was no wider than the Mediterranean today. It had a very weak connection with the North Atlantic. And through this very narrow strait, the same thing happened. A vast salt layer was deposited that's now preserved beneath the offshore margins of Angola and the offshore margins of Brazil, dating back to called the Aptian, 120 million years ago. A similar huge thick salt deposit accumulated on the floor of the Gulf of Mexico 190 million years ago. And another giant salt deposit beneath the North Sea and regions of northern Germany and eastern England, the Zechstein in the Permian period, even much more ancient. So there are giant salt deposits of similar volumes, 1 million cubic kilometers. In fact, enough salt that the Mediterranean took away 3% of the salt of the entire global ocean.
There was a question from Gus Correa, but I understand that that's now been answered by the answer to another question. So I think we're running out of questions. If anybody has a quick burning question, please get it in. If not, it might be time to wrap up.
Well, what I'd like to communicate to all young earth scientists, or those that may wish to go into a career, there's lots more to be discovered. Lots more.
Right, on that note, then I think that's all we have time for. Thank you so much, Bill, for joining us today and giving us that fascinating talk. The next lecture is taking place in person at Burlington House on the 7th of November. It will be by Jenny Barkley, and it's entitled The Stories We Tell About Volcanoes, Why It Matters and When They Erupt. And Becky will post the link in the chat before we leave today. So thanks once again, and yeah, see you next time.
Thank you, everyone, and thank you, Bill. I'll send a follow-up email with a link because I know it can be a bit difficult clicking on links in the chat. So thank you all and have a good evening. Okay, and rest of your day to the US visitors.
Yeah.